Hello there, welcome to opti505r. This is extra lecture B. The topic for lecture B will be speckle. Now with speckle, to really analyze speckle, you have to do a pretty thorough statistical analysis. In this class, we're not really assuming that the students have a strong background in statistics. So what we'll have to do is skate through a few of the things and give an explanation that should be understandable, at least on a heuristic basis. We will provide some mathematics, but the full analysis requires some statistical development. But this should give you an appreciation. It's kind of a fun topic. So what I'd like to do is start with the reference here that I'll be using is from Hariharan, a book called Optical Interferometry, chapter 14 of the particular edition that I was using, looking at. And what we've studied so far in class is with our interference, and then the final lecture will actually be about thin film reflection and transmission. We're always assuming that the optical surfaces are nice and smooth and perfectly reflecting or transmitting. So this is called a specular reflection. The reflection does not change the wavefront, and there's no wavefront distortion. Now that's completely unlike, for example, the surface of this paper, which is a rough surface, where even if we take a laser beam with a perfect wavefront into it, then the reflection will be a very distorted surface, or wavefront, very disturbed with respect to the perfect uniformity of the input plane wave. Now this can be modeled in several different ways. One of the ways that I like to think about it is that the surface is very rough. And these little rough surfaces act sort of like mirrors. But each little facet presents a different phase in reflection. Remember, this is the optical phase in reflection is twice the depth of the feature in the material, corrected for the cosine of the angle of incidence. And so the incident phase is then the incident phase fronts here are distorted according to the topography of the surface roughness. Usually the surface roughness has some correlation length that I've labeled here as lambda. But basically what we're talking about is the far field diffraction from a bunch of random wavelets here with random phase. Basically we're taking a plane wavefront and making the reflected wavefront a combination of randomly phased wavelets from the surface. So we're going to assume that that reflected wavefront is the sum of the complex amplitudes of the diffracted waves from the little microscopic mirrors. And if we write that into an equation form, we have that the reflected amplitude is 1 over n. N is the number of beamlets, times the magnitude of each individual beamlet times its phase. Okay? And here I've used a slightly different convention for the phase than we've used in the past. We used plus, minus is just as good for this development. Now, we're going to assume that the amplitude and phase of those components are statistically independent, little independent radiators. They're coherent, but the phase is independent. Okay? And the range of phase shifts of each of those wavelets goes between 0 and 2 pi. It can be anywhere within 0 and 2 pi uniformly. And now we take it turns out that under those conditions, if you've had a course in optical statistics, you know that the complex amplitude and phases of, the real and imaginary parts of that complex reflected wave obey Gaussian statistics. Now, the Gaussian statistics imply that the average amplitude of that reflected wave is 0 if the phase goes between 0 and 2 pi. And the phase has a uniform circular distribution. Now, it turns out with this kind of a surface, if we take a point detector, and the point detector here is a physical detector. It can be a normal silicon cell maybe with a pinhole in front of it. And we take a measurement plane here. A is a function of x and y on the axis of the plane here. And move that point detector around. Then what we're going to do is we're going to measure the current. Okay? And what we're going to keep track of is as we move it over the plane, how many times do we see a certain irradiance value? Well, if we histogram those irradiance values, and we come up with an exponentially decaying distribution like this, where the vertical axis represents the number of times that we found that irradiance value. And the horizontal axis represents the magnitude of the irradiance. So although the average amplitude is 0, the average irradiance is equal to 2 times the variance of this Gaussian, where the Gaussian is represented by e to the minus I over 2 sigma squared. Okay? So we have this exponential fall off. Average irradiance here is twice, just the denominator here. Okay? So, how big are the speckles? Well, hey, is this right? What we're saying is that we've got this random distribution of light. So what I've got is a little demo, and hopefully the demo will work for us, where what I'm going to do first, Molly, is just use the focused case. We'll get to that other case here at the end of the class. But what I'm going to do is illuminate this paper with a laser. See, I've got a laser. See if I can shine it to you guys and blind you. See which one are you operating on. That one? Ah, you see it? Okay. All right. So it's on. And I'm just going to illuminate the paper. And sure enough, you see little speckles there. Okay. And that's what we're talking about, that little variation. The amplitude of the wavefront is actually Gaussian. The little speckles are not in the wave coming out of the laser. That's a result of reflecting off that rough piece of paper. Okay. So, oh yeah, you're never supposed to shine a laser beam, especially into the eyes of low-flying airplanes. Just to give you a little safety lesson. Okay. So we want to what makes those speckles so large? Okay, what determines their size? Well, it turns out that if we take the autocorrelation of the intensity, then in the speckle pattern, the result is, and again, this is the part where we're missing the statistical background to really go through the details of this. But the result is that it's the average irradiance squared out in front times 1 plus the ratio of the Fourier transform of the unspeckled illuminated area. In other words, just got a laser beam here with a Gaussian coming out of it. It's just the Gaussian. Or it could be a square or whatever maybe size the rough object is, depending on how big we're illuminating it with a laser beam. And it's that irradiance. Fourier transform. Okay, so this is just a Fourier transform representing the observation and illumination planes. And that's just normalized by the amount of power that's illuminating the surface. So that's just the normalized Fourier transform of the size of the illuminated surface, where the transform variables are just like we studied in Chapter 5, the Fraunhofer transform variables, x over lambda z, where x is the observation plane. So it varies as z. The farther we get away from the illuminated surface with our observation, the larger the speckles. The smaller the size of the illuminated source, or illuminated area, the larger the speckles. And it also changes with wavelength, etc. Okay, so we can find the average size of the speckles by just Fourier transforming the illuminated object. Okay, now here's an example where we take a laser beam, plane wave, illuminating a square object of side length L, and we propagate over a distance z, and the size of the speckle there is some finite size. So here I've labeled it as delta x and delta y. So if we apply our equation and take our Fourier transform, we just have two sinks, one for each direction, x and y. And so they have the same arguments because L is the same length. It's a square. So the size of the speckle then, if we just illuminate where the sink pattern goes to 0, the sink pattern then is just lambda z over L. So as L gets larger, the speckle size gets smaller. As z gets larger, the speckle size gets larger. As lambda gets larger, the speckle size gets larger. Okay, and vice versa. Okay, so that's a really, really handy thing to keep in your hip pocket, just as a suggestion for you. Now, what happens, that's a very simple system where we have just a direct propagation between the illumination plane and the observation plane. What about an optical system? Well, an optical system really isn't that much different. Okay, let's say we have a laser beam illuminating a rough object. Now, actually, there's a lot to this that I'm glossing over a lot of it, but I'm just giving you some of the high points that are, generally applicable. And you have to take, for example, if the object is a fractal surface, there's a lot of things to consider. If the optical system has aberrations, there's other things to consider. We've written several papers on this recently, actually. But let's just take the ground zero, okay, because you really don't have the background, or I'm not assuming that you don't have the background to, and we don't have the time to talk about a lot of the details there, but maybe we can do that in an advanced class. So if we take a laser beam and illuminate a rough object, then what we've got propagating from the object is this random amplitude and phase distribution. Well, that random amplitude and phase distribution is present in the entrance pupil. If you take the Fourier transform of a random distribution, you get another random distribution. And that's isomorphically mapped, we're assuming, into the exit pupil reference sphere. And then we've got a Fourier transform to the object. So effectively, in the exit pupil, what we have is a random distribution of phase and amplitude. And when we Fourier transform that, it's like a speckle pattern. It's like the Fraunhofer pattern that we had in the first case, where we just looked at the rough object being illuminated and looked at some distance away from that pattern to the observation plane. It's just, again, it's just a Fourier transform. So the Fourier transform of the size of the distribution in the pupil at the image plane, assuming, we've got to be working with coherent light, well, that's just the coherent point spread function. So it turns out that in an optical system, the size of the speckle that we observe are just equal to the width of the point spread function. Very simple result. And now in our system here, what we've got is I've got a rough object, and Molly is viewing that through the optical system. We've got some room lights here, so we can actually see the image of the object through incoherent illumination. But then when I shine the laser beam on this object, she's also viewing that through the system coherently. And so the size of her system in the focal planes and such is just like I've described here. So we saw in the speckled image that Molly presented to you, the size of those speckles was Molly's point spread function. Okay, that was the size. Those speckle sizes determined how good she was focusing on my paper, and the iris and the focal length of the lenses in there, and how they were set up. I think that's pretty interesting. Okay, now, this is an interference class also, so we have to do some work, I guess. We can actually do interferometry with speckle. So we're going to go back through a little bit of basic phenomena here. And then we're going to be talking about a couple of the applications. Those include looking at vibrating surfaces and different types of displacement. In-plane displacements, that's the focus direction. And, out-of-plane displacement and then vibration like we did with the rotating membrane in holography in Lecture A, extra Lecture A. And then something called stellar speckle interferometry. And then we're going to talk very briefly about electronic speckle pattern interferometry. And also I'm going to show you a demo with Molly's camera where if you do have a laser beam like this, you can tell if you're nearsighted or farsighted. And then I'm going to leave it up to you to explain why. So, well, speckle pattern. We just saw an example of one a minute ago. It's got to be a rough surface, and you've got to be some distance away. Basic problem here is that we've got a rough surface through an optical system. We're going to have different PSFs, and the phase of those PSFs, coherently illuminated surface, are random. So we're looking at that combination of random interference or random phase interference from those different PSFs. Now, if we have a vibrating rough surface, vibrating diffuse surface, then we're going to have the same kind of J0 squared Bessel function we had before in holography when we combine that through an interferometer, because an interferometer is just one way to produce a holographic pattern, if you want to think about it that way. When we look at these vibrations, we're going to see the contrast change, just like we did with the holographic lecture, according to this J0 Bessel function. So we can actually see between the plane being stationary and the plane vibrating, we can take this information then and translate it into first of all, calculate the contrast of the fringes here in the speckle, and with the rough surface now, actually calculate the amplitude of the vibration according to the contrast of the speckle. So that was in the z direction, out of plane vibration. Now what about if we change the object in plane vibration? Now this is the technique to do that, where we take our rough object and we illuminate it. Here it's shown as a transmission. Of course, you can make this into an interferometer if you'd like. Each little speckle point is going to produce or each little rough point is going to produce a spherical wave, and the combination of all those spherical waves produce the speckle pattern that we see in this case, this is kind of an old slide, a photographic plate. We could also put a camera here in modern times. So the idea is we take this rough surface, keeping the same reference wave, but now we displace the, we take the photographic plate and we, hold on a second. Oh yeah, okay. So take the photographic plate, develop it, put it back, just like we had before, okay? And now what we do is keep the same illumination wave. So we have a developed pattern of speckle on our photographic plate, which would be regions, very small regions then of transmitted amplitude where the speckle irradiance was high, and then where the speckle radiance was low. Oh, I'm sorry, it's just the opposite. Sorry about that. With the D log H curve that I showed in the holography lecture, what we would have is the bright speckle producing a dark spot on the holographic plate and or on the photographic plate, and then dark speckle would produce a transmitted field. So if we take that same plate and replace it in the same geometry, but then behind the plate here put a lens and look at the focal length of the lens, and we have the Fourier transform of the plate, which is not too interesting until the plate is translated. And when the plate is translated, then we have the same speckle pattern, only shifted here. Here. Okay. So we have like a Young's double pinhole. For every place there was a speckle here, now there's a shifted speckle point. So what we have is a whole combination of Young's double pinhole features in our photographic plate, or at the photographic plate plane, which produce Young's double pinhole fringes in the observation plane. And you can see that very clearly with a, this is a photograph of that situation where we've recorded the speckle on a plate and then kept the same geometry but displaced the object. And then when we displace the object, the little speckle patterns move slightly, producing the multitude of Young's double pinhole interferometers, and we get these straight line fringes. Well, we can also, instead of just displacing the object simply, like here is a linear motion, we can also do a vibration pattern, and we get these very interesting speckles according to the Fourier transform of the motion. Okay, with speckle, we have an effect in the atmosphere, which this technique actually was important. It's kind of important historically. I don't know that it's really done much anymore, but before the use of adaptive optics, let's just put it that way, the astronomers wanted to resolve stars looking through the atmosphere, but they had a problem. And that problem was that the atmosphere limits the resolution to about 1 arc second. And that's because in the layers of the atmosphere, the wind and the atmospheric layers are always moving around. And when they're moving around, the coherent, that's like a random phase surface, where the size of the coherent areas, you can think about it maybe as the size of the speckle, is only about 10 centimeters, about 4 inches. These huge telescopes, but they had this random phase in their pupil. Now, if you take the image of a star, what you're going to have, if the exposure time is less than the period of the turbulence, maybe 1 millisecond, then you're going to see a lot of speckle in the image. And there's an example down here. That's an example of a speckled star. Okay. And the speckle size, as we've talked about, is determined by the wavelength and the telescope diameter, basically the diffraction limited resolution at the image plane. The speckle information is limited by the limit of the telescope, not the atmospheric turbulence. Remember, the size of the individual speckles is the size of the point spread function of the telescope. But there's all this stuff due to that random phase nature in the pupil. So what astronomers used to do, may still do it, I don't know, is to take a very large number of short exposure photos of the object where each photo is taken for a different, in a different time, so the atmosphere has changed a little bit between exposures. And then you take the Fourier transform of each photograph to obtain different diffraction patterns. You add the square modulus of the diffraction patterns of all the photos, and then take the Fourier transform of the ensemble of the average of the diffraction patterns, and the result is the autocorrelation. You don't exactly get an image back, but you get the autocorrelation of the diffraction limited image of the object. So here's some results. And you might be able to see these, Molly. I might ask you to move in just a little bit more. That's good. Thanks. Okay. So here we have an object. Here I have a single star and a single photograph and its Fourier transform. Then the sum, as we discussed, of all the two-dimensional Fourier transforms. And then the Fourier transform of the sum. So you see a single point gives a single point image in the process. Okay? So what you receive out of each photograph of the star through the telescope, although, is this distorted image, but it's really this little point object. But that's the autocorrelation of this. So it's a little bit larger, than the object itself, maybe a factor of 2. Okay. Now, what if we have a double star? If we have a double star, we get a really ugly individual photograph. We get a Fourier transform that includes the Young's fringes, so we see a little bit of structure there in the fringes. Take the sum of the 2D Fourier transforms of the ensembles there, and what we get with the autocorrelation then is we get a big bright spot in the center, and then we see the in the outside. That's very interesting. Okay, and here's another couple of examples. A little bit wider separation of the stars gives us wider separation here, closer Young's fringes. A big star gives us a big blob. So, and out of this mess, this is what we get. So that's pretty cool. So that was a technique that was used before adaptive optics. And one more subject before we have a little bit of fun. So now I mentioned that with holography, the advent of these very high resolution, high performance cameras really holds a lot of exciting potential. We can also say the same thing about electronic speckle pattern interferometry. So here what we're doing is we're replacing those electronic plates with a high resolution camera. And this work actually was done by Catherine Kreth here at the university some number of years ago for the early versions of these cameras. Things have gotten a lot better since then. Okay. So the idea is to get real-time measurements. We don't have to work with photographic plates, emulsions, envelopment, that sort of thing. And the minimum speckle size, then, as we talked about earlier, is actually just the point spread function of the camera that we're using. And then what we can do is use these powerful computers that we have now to perform computer analysis of the speckle data. And I'm not going to go into a lot of detail about that. Again, the analysis requires some knowledge of statistics. But here's some beautiful patterns that were obtained for different vibrational modes of vibrating plates. Okay, so now we get to have a little fun. And what I'm going to do is I'm going to stand up, and I'm going to ask Molly to focus in on maybe just this little section right here. Molly, would be good if we could zoom in there. And that's going to be kind of our reference plane. I'm going to ask her to go in, zoom in just a little bit more and focus. Very, very good. Try to get a sharp focus. Okay. So now remember what we've said about the size of the speckle. Now that you know a little bit more background, I'm going to take my laser beam. Oops. And I'm moving it with my shirt tail. Hold on a second. And I'm holding my laser beam up here, and we see the size of the speckle. Pretty small. She's got pretty good resolution on her camera. But now if we defocus the camera, the size of the speckle is going to change. So Molly, I'd like you to defocus the camera. And as she's defocusing, you can see that the size of those speckle are getting larger. Do you see that? And that's because the point spread function of her camera is getting wider also. Okay, now I'm going to play a trick on you. I'm going to move the spot, and I want you to observe the direction that the speckle are moving relative to the direction of my motion. So you see there? It's kind of going in the opposite direction, isn't it? See that? Opposite direction is the movement. Now I'm going to play a trick on you. What if we go defocus in the other direction about the same amount? We should have about the same size of speckle. So Molly, could you go back through focus? See the speckle getting smaller and smaller and smaller. And now she's going to go back through focus the other way. Beautiful. Speckle get larger. And now what I want you to observe is the direction of the speckle as I move the spot. So what's happened? The speckle are now moving in the same direction as I'm moving the spot over the surface. Okay, well, we understand why the speckle gets larger, but why the heck does it move in the first place? And why, okay, Molly, we'll have a face view now. Why does it move in opposite directions depending on whether I'm focused too far or focused too closely to the camera? Now, you can actually use this test to determine if you're nearsighted or farsighted. So I encourage you to go out and play with your laser pointer, maybe expand the beam a little bit with a weak lens, and try it with your glasses on, with your glasses off if you're nearsighted or farsighted, and see which way we go there. And I'll leave that as a fun exercise for you to determine why that happens. And what I want you to do is kind of keep this picture in mind, that as the speckle expands, it's kind of like a little cone, okay, where each little speckle kind of expand in size, just like diffraction from a small object. So you've got a collection of these little cones as the total of the speckle pattern. And if you keep that in mind and think about what happens through the eye, you might get a good feeling for why those speckle are moving in the direction that they are. Okay, so this has been a short but fun little introduction to speckle. It's a great topic, and if you're interested in that, I hope that you get some background in statistics if you don't already have it, and then maybe we can do some other more advanced stuff in another class. So thank you very much. That's it for speckle.